Have you ever noticed how some places on Earth feel completely unreal, shaped by ancient and extreme forces? In this episode of Unearthed Secrets, we explore lost landscapes formed by time, isolation, and change. Like and subscribe, and tell us where you're watching from and what time it is for you right now. The lake that filled a void. High in the Cascade Mountains of southern Oregon, there's a lake so deep and blue that it seems disconnected from the world around it. Steep cliffs drop directly into still water. No rivers flow in. No streams flow out. Snow lingers on the rim well into summer, and silence settles quickly when wind dies down. From the edge, it feels less like a lake and more like an opening, an immense basin holding water that has nowhere to go. This is Crater Lake, the deepest lake in the United States and one of the clearest natural bodies of fresh water on Earth. The Crater Lake sits at an elevation of approximately 1,683 meters above sea level within Crater Lake National Park. The lake fills the caldera left behind by the collapse of Mount Mazama, a volcano that once towered over the landscape. Today, nothing of that original peak remains. In its place is a nearly circular basin, 8 kilometers wide and more than 590 meters deep, holding water of extraordinary clarity and color. Crater Lake is not a crater in the usual sense. It was not formed by a meteor impact, nor by a simple volcanic explosion that left a bowl behind. It is the result of one of the most violent volcanic events in North America during the last 100,000 years. The story begins roughly 7,700 years ago. At that time, Mount Mazama was a massive stratovolcano, rising more than 3,700 meters above sea level, taller than today's Mount Hood. It had grown through repeated eruptions over hundreds of thousands of years, layering lava, ash, and volcanic debris into a towering cone. For long periods, it appeared stable, dominating the skyline of the southern Cascades. Then, Mount Mazama erupted catastrophically. The eruption began with towering ash columns that blasted material tens of kilometers into the atmosphere. Pumice and ash rained down across vast areas of what is now Oregon, Northern California, and beyond. Pyroclastic flows, fast-moving clouds of superheated gas and volcanic debris, raced down the mountain slopes, destroying everything in their path. As magma was expelled, the underground magma chamber emptied. With its support gone, the summit of Mount Mazama collapsed inward. Rather than exploding outward, the mountain imploded. The top fell into the void below, creating a massive caldera where the peak once stood. The eruption reshaped the region permanently. Thick layers of ash altered river systems. Forests were buried. The landscape cooled and settled into its new form, a giant depression encircled by steep volcanic walls. For a time, the caldera was empty. Rain and snow began to fall into the basin almost immediately, but filling it took centuries. Crater Lake has no rivers feeding it. Every drop of water in the lake comes from precipitation. Snowfall in winter, rain in warmer months. Likewise, the lake has no surface outlet. Water leaves only through evaporation and slow seepage through porous volcanic rock. This balance is delicate and precise. Over hundreds of years, the lake level rose until it reached equilibrium. Today, Crater Lake is remarkably stable, its level fluctuating only slightly from year to year. What sets Crater Lake apart visually is its color. The water appears an intense, almost unreal blue. This is not due to algae or minerals, but to purity. Crater Lake is one of the clearest large lakes in the world. With very few nutrients entering the system, there is minimal plankton growth. Sunlight penetrates deeply, and shorter blue wavelengths scatter back to the eye, producing the lake's signature color. On calm days, the surface reflects the surrounding cliffs perfectly. On windy days, waves ripple across the deep blue, but the water remains clear enough that visibility can extend more than 40 meters below the surface in some areas. The caldera walls rise steeply from the lake, reaching heights of more than 600 meters above the water. These walls expose layers of volcanic rock, lava flows, ash, deposits, and pumice, each recording a phase of Mount Mazama's construction and destruction. The rock is unstable in places, prone to rockfalls and erosion, reminding visitors that this landscape is still evolving. Within the lake itself are two prominent features. The first is Wizard Island, a cinder cone that rises more than 230 meters above the water's surface. Wizard Island formed after the caldera collapse, when volcanic activity resumed on a smaller scale. Lava erupted from vents on the caldera floor, building the island gradually. Today, it stands as evidence that Mount Mazama's story did not end with its collapse. The second feature is Phantom Ship, a jagged rock formation that resembles a ghostly sailing vessel when seen through mist. It is one of the oldest exposed rocks in the caldera, a remnant of pre-collapse Mount Mazama that resisted destruction. Crater Lake is not a dormant system. Though the volcano beneath is considered inactive rather than extinct, there is ongoing geothermal activity deep below the surface. Earthquakes occasionally occur, and hydrothermal vents exist beneath the lake, though they do not significantly affect water temperature or chemistry. The lake's isolation makes it a natural laboratory. Scientists study Crater Lake to understand volcanic processes, water chemistry, and ecological dynamics in nutrient-poor systems. The absence of inflowing rivers means the lake responds slowly to environmental change, preserving long-term records in its sediments. Human history at Crater Lake extends back far beyond European arrival. Indigenous peoples, including the Klamath tribe, lived in the region long before the eruption of Mount Mazama. Oral traditions describe a great battle between spirits of the sky and the underworld, ending with the collapse of a mountain and the formation of a deep, sacred lake. These stories are remarkably consistent with geological evidence, suggesting that the eruption was witnessed by human ancestors and preserved through oral history. For the Klamath people, Crater Lake was not a place to be used casually. It was revered and feared, associated with powerful forces. Even today, it holds cultural significance. European American awareness of Crater Lake came much later. In 1853, a group of prospectors stumbled upon the lake while searching for gold. Struck by its beauty and depth, they called it Deep Blue Lake. Over time, its uniqueness became more widely recognized. In 1902, Crater Lake National Park was established, becoming the 5th national park in the United States. Protection came relatively early, preventing development that could have altered the lake's fragile balance. Access to the lake is carefully managed. There are no private boats allowed. Swimming is permitted only in designated areas. Fishing is regulated. These measures help maintain water quality and ecological stability. Despite its clarity, Crater Lake is cold. Even in summer, surface temperatures rarely exceed 17 degrees Celsius, and deeper water remains near freezing. The depth creates thermal layering that persists year-round, influencing circulation patterns and oxygen distribution. Winter transforms the lake entirely. Snow accumulates heavily on the rim, often more than 10 meters annually, making the area one of the snowiest places in the United States. Roads close, silence deepens. The lake becomes a dark blue disk surrounded by white, its surface partially frozen near the edges. Climate change poses uncertainties for Crater Lake's future. Changes in snowfall, temperature, and evaporation could alter the lake's balance over time. Increased wildfire activity in surrounding forests could introduce ash and nutrients, affecting clarity. For now, the lake remains resilient, but its isolation makes any changes more significant. What makes Crater Lake compelling is not movement or danger, but absence. There's no inlet carving a valley, no outlet spilling water downstream. The lake exists entirely within its own boundaries, held in place by gravity and time. Standing at the rim, it is difficult to grasp the scale. The surface looks close, but it is far below. The water appears flat and calm, but it fills one of the deepest basins on the continent. The mountain that created it is gone, erased by its own eruption. Crater Lake is a landscape shaped by loss. A mountain vanished. A void remained. Water arrived slowly and stayed. It does not erupt. It does not flow. It reflects. In the Cascades of Oregon, Crater Lake remains one of the clearest reminders that destruction and creation are often the same process, separated only by time. A volcano collapsed, and in its absence, something quieter formed, still, deep, and enduring. The lake is not a scar. It is a record of collapse, patience, and balance, held in blue water, waiting, as it has for thousands of years, within the walls of a mountain that no longer exists. The island that evolved alone. In the northwest Indian Ocean, where the Arabian Sea meets the Gulf of Aden, there's an island that appears detached not only from continents, but from time itself. Trees rise with swollen trunks and bare branches, like something imagined rather than grown. Plants follow shapes found nowhere else on Earth. Coastlines fracture into cliffs and caves. Inland plateaus stretch beneath relentless sun and wind. This is Socotra, an island so biologically distinct that it is often described as the most alien place on the planet, despite being entirely natural. The Socotra Island belongs politically to Yemen, but geographically it sits far from the mainland, about 380 kilometers south of the Arabian Peninsula and roughly 240 kilometers east of the Horn of Africa. This isolation is not recent. Socotra separated from the supercontinent Gondwana more than 20 million years ago. Since then, it has remained largely cut off from surrounding landmasses, allowing life to evolve independently, shaped by harsh conditions and long-term isolation. That separation is the key to everything that makes Socotra unusual. More than a third of the plant species found on Socotra exist nowhere else on Earth. Some estimates place endemism even higher. This level of uniqueness rivals that of the Galapagos Islands, but with a far older evolutionary timeline. While the Galapagos emerged from volcanic activity relatively recently, Socotra is ancient, a fragment of continental crust that drifted away and remained exposed. The island's most famous symbol is the dragon blood tree, Dracana cinnabari. These trees grow with thick trunks and umbrella-like canopies, their branches splitting repeatedly as they rise. From above, forests of dragon blood trees resemble clusters of green mushrooms. Their shape is not aesthetic, it is survival. Rainfall on Socotra is scarce and unpredictable. The umbrella canopy captures moisture from fog and mist, channeling it down the trunk to the roots. The dense crown also shades the soil beneath, reducing evaporation. Over millions of years, this form proved successful, and the species endured. The name dragon blood comes from the tree's red resin, which seeps out when the bark is cut. For centuries, this resin was harvested and traded across the ancient world. It was used as a dye, a medicine, a varnish, and an incense. Roman texts reference it. Medieval apothecaries sold it. Its value tied Socotra into trade networks long before modern borders existed. But the dragon blood tree is only one part of Socotra's strangeness. Bottle trees, with bulbous trunks that store water, dot the landscape. Shrubs grow in rigid, skeletal forms. Succulents cling to bare rock. Many plants appear exaggerated, distorted, or unfinished, traits shaped by extreme dryness, poor soil, and constant wind. The island's climate is unforgiving. Temperatures are high year-round. Monsoon winds batter the coastline seasonally, making sea travel dangerous and isolating the island further. Rain, when it comes, often falls in brief, intense bursts that quickly run off rocky terrain. Fresh water is scarce. Many organisms survive by capturing moisture from the air, rather than relying on rainfall. This has driven evolutionary paths rarely seen elsewhere. Socotra's geology reinforces this isolation. The island is composed largely of limestone and granite, eroded into plateaus, gorges, and caves. Karst formations dominate parts of the interior, creating sinkholes and underground channels. Coastal cliffs drop sharply into the sea, limiting access and shaping settlement patterns. Unlike volcanic islands, Socotra was not built upward by eruptions. It was left behind by tectonic movement, then sculpted slowly by erosion. Its mountains are not dramatic in height, but they are ancient, worn down over immense spans of time. Human presence on Socotra dates back thousands of years. Archaeological evidence suggests habitation as early as the first millennium BCE. Its position along maritime trade routes made it a stopping point for sailors navigating between Africa, Arabia, and India. Greek, Roman, Arab, and Indian traders all knew of Socotra. Historical accounts describe it as a place of valuable resins, strange plants, and isolated communities. Despite this contact, the island never became heavily colonized or transformed. Its harsh environment limited large-scale settlement. The people of Socotra, known as Socotrans, developed a culture closely tied to the land. Many live semi-nomadic lives, herding goats and fishing along the coast. Their language, Socotri, is distinct from Arabic and preserves ancient linguistic features. For generations, traditional knowledge governed resource use. Trees were harvested carefully. Grazing followed seasonal patterns. Survival depended on balance. That balance is now under strain. In modern times, Socotra's isolation has been challenged. Roads, ports, and increased contact have brought change. Livestock numbers have grown, putting pressure on vegetation. Invasive species threaten native plants. Climate change adds further uncertainty, altering rainfall patterns and increasing stress on fragile ecosystems. Recognizing its global importance, Socotra was designated a UNESCO World Heritage Site in 2008. This status highlights its role as a living archive of evolution, an ecosystem that reveals what happens when life is allowed to diverge over millions of years with minimal interference. Yet, protection is complicated. Yemen's ongoing conflict has limited international oversight and conservation efforts. Political instability affects governance, resources, and long-term planning. Socotra's future remains uncertain, caught between preservation and change. Wildlife on the island mirrors the uniqueness of its plants. Most of Socotra's reptiles are endemic. Birds include species found nowhere else, adapted to the island's terrain and climate. Insects, many still poorly studied, fill ecological roles shaped by isolation. Large mammals are absent. There are no native predators like lions or wolves. The ecosystem evolved without them, making it especially vulnerable to introduced species and overgrazing. The surrounding seas are equally rich. Coral reefs fringe parts of the island, supporting diverse marine life. Strong currents mix waters from different regions, creating unusual combinations of species. Fishing has sustained communities for centuries, though modern pressures are increasing. Visually, Socotra feels unreal. Landscapes appear sparse but intentional. Trees cast sharp shadows across bare ground. Rock formations frame empty horizons. There's little softness here. Everything looks adapted, refined, and specific. Silence dominates the interior. Wind replaces sound. The absence of dense vegetation amplifies scale. The land feels open and exposed, as if nothing is hidden. At night, the island becomes darker, still. With little artificial light, the sky overwhelms. Stars fill the horizon. The Milky Way stretches clearly overhead. The sense of separation deepens, not just from continents, but from modern life. Socotra is often described as alien, but that description reflects human bias rather than reality. The island is not strange because it is unnatural. It is strange because it followed a different path. While continents collided, glaciers advanced, and species competed elsewhere, Socotra remained apart, refining solutions to survival in isolation. In this sense, Socotra is not behind or ahead of the rest of the world. It is parallel. Scientifically, the island is invaluable. It provides insight into speciation, adaptation, and resilience. It shows how ecosystems respond when competition is limited but resources are scarce. It demonstrates how form follows function in extreme environments. Every tree shape, every growth pattern, every survival strategy is a response to pressure, wind, drought, heat, isolation. Nothing here is ornamental. Everything serves a purpose. And yet, the result feels artistic. The dragon blood tree's silhouette at sunset. Bottle trees standing alone on rocky slopes. White limestone cliffs against blue sea. These images circulate widely, often stripped of context. But without understanding the processes behind them, the visuals risk becoming novelty rather than knowledge. Socotra is not a theme park of oddities. It is a fragile system built over millions of years. Once disrupted, it cannot be easily restored. Evolution at this scale does not repeat on human timelines. The island's greatest threat is not sudden destruction, but gradual change. Overgrazing removes young trees before they mature. Development fragments habitats. Climate shifts alter delicate balances. Loss here would be permanent. Socotra does not regenerate quickly. It remembers. Standing on the island, it becomes clear that isolation can be both a shield and a vulnerability. It allowed life to diversify in peace. It now makes that life harder to protect. In a world increasingly connected, Socotra remains a reminder of what separation can produce. Not emptiness, but richness. Not simplicity, but specialization. The island does not shout its importance. It exists quietly, shaped by wind and time, carrying species that represent millions of years of uninterrupted evolution. Socotra is not a lost world. It's a living one. And as long as it remains intact, it will continue to show what the Earth can create when it is allowed to work alone, patiently, relentlessly, and without regard for human expectation. The stone forest that cuts the sky. In western Madagascar, far from major cities and paved roads, there is a landscape so sharp and fractured that it seems actively hostile to movement. Thousands of limestone blades rise vertically from the ground, packed tightly together like the teeth of a giant saw. There's no soil between them, no flat ground, only stone, split, eroded, and sharpened into points that can slice skin and tear clothing. From a distance, the formation looks solid and immovable. Up close, it reveals endless gaps, crevices, and voids beneath the surface. This is the Tsingy de Bemaraha, one of the most extreme karst landscapes on Earth. The Tsingy de Bemaraha lies within the Bemaraha National Park, a protected area in western Madagascar. The word Tsingy comes from the Malagasy language and roughly translates to where one cannot walk barefoot. It is not a metaphor. It is a practical warning. The limestone pinnacles are razor sharp, formed by dissolution, rather than fracture, and they make ordinary movement impossible. Tsingy de Bemaraha is not a mountain range, nor a canyon system, nor a single rock formation. It is a limestone plateau that has been dissected vertically over millions of years, turning solid rock into a three-dimensional maze of spikes, towers, and voids. To understand how such a landscape formed, it is necessary to return to a time when Madagascar looked nothing like it does today. Around 200 million years ago, Madagascar was still part of the supercontinent Gondwana. Shallow seas covered much of the region, depositing thick layers of calcium carbonate from marine organisms. Over time, these sediments hardened into limestone. When Gondwana broke apart, Madagascar drifted away, carrying these limestone platforms with it. For millions of years, the limestone remained relatively intact. Then tectonic uplift raised the plateau, exposing it to air and rain. This marked the beginning of the process that would create the Tsingy. Limestone is soluble in weakly acidic water. Rainwater absorbs carbon dioxide from the atmosphere and soil, forming a mild carbonic acid. When this water seeps into limestone, it slowly dissolves the rock along fractures, joints, and bedding planes. In most karst landscapes, this process produces caves, sinkholes, and rolling hills. In Bemaraha, conditions align differently. The limestone here is thick, pure, and heavily fractured. Rainfall is seasonal but intense. Water drains quickly through cracks, focusing erosion downward rather than outward. Over immense spans of time, vertical fissures widened, while the remaining rock sharpened. Instead of rounded hills, the plateau fractured into blades. Erosion did not remove the rock evenly. It attacked weaknesses, carving deep chasms while leaving narrow ridges behind. As dissolution continued, those ridges became thinner and sharper. Eventually, the surface transformed into a field of stone spikes, some reaching heights of 30 meters or more. What makes the Tsingy unique is its verticality. The landscape is not just rough, it is fundamentally three-dimensional. Beneath the spikes lies an extensive network of caves, tunnels, and chambers. The surface is only the visible edge of a much deeper system. From above, the Tsingy de Bemaraha resembles a forest of stone needles. From within, it feels like a labyrinth. Light filters through narrow gaps. Shadows fall sharply. Sound behaves strangely, echoing unpredictably through stone corridors. Movement through this terrain without equipment is nearly impossible. Modern access relies on ladders, harnesses, suspension bridges, and fixed cables. Even with these aids, traversal is slow and deliberate. For much of history, this difficulty kept the Tsingy largely inaccessible. Human presence in Madagascar dates back at least 1500 to 2000 years. Early settlers arrived by sea, likely from Southeast Asia and East Africa. They brought agriculture, livestock, and fire. Much of Madagascar's landscape was altered dramatically as forests were cleared and ecosystems changed. The Tsingy, however, resisted this transformation. The sharp limestone made farming impossible. Grazing animals could not navigate the terrain. Large-scale settlement never took hold. As a result, the Bemaraha Plateau became a refuge, not only from human activity, but for life itself. This isolation allowed unique species to survive. Madagascar is already famous for its biodiversity and endemism. More than 90% of its wildlife exists nowhere else. Within the Tsingy de Bemaraha, this pattern intensifies. Lemurs, Madagascar's iconic primates, live within and around the Tsingy. Some species use the stone forest as protection from predators. Others move along the edges, feeding in nearby forests and retreating into the limestone maze. Reptiles thrive here as well. Geckos, chameleons, and snakes exploit the warm rock surfaces and hidden crevices. Many species are endemic to the region, adapted specifically to the microhabitats created by the tsingy's extreme structure. Birds nest in inaccessible ledges, bats roost deep within caves, insects occupy narrow ecological niches, living in cracks where moisture and temperature remain stable. Plants too have adapted in remarkable ways. Soil is scarce on the tsingy surface. Where plants grow, they do so in pockets of sediment trapped between rocks or within fissures. Roots extend deep into cracks to access moisture. Some species cling directly to stone, drawing nutrients from mineral deposits and organic debris. The result is a fragmented but resilient ecosystem, layered vertically as much as horizontally. Rain behaves differently here. Instead of flowing across the surface, it disappears almost immediately into the rock, draining into underground systems. This creates dry conditions on the surface even during wet seasons, while caves below may carry water long after rainfall ends. These underground waterways eventually feed rivers that emerge far from where the rain fell. The tsingy acts as a vast natural filtration system, channeling water invisibly through stone. From a scientific perspective, Tsingy de Bemaraha is one of the most extreme examples of tropical karst topography in the world. It provides insight into how limestone landscapes evolve under specific climatic and structural conditions. The park is divided into two main areas: the Grand Tsingy, where the formations are tallest and most dramatic, and the Petit Tsingy, which is more accessible but still rugged. Both areas reveal different stages of erosion and formation. The age of the Tsingy surface is difficult to pinpoint precisely, but the process that created it likely spans millions of years. This is not a sudden or catastrophic landscape. It is the result of persistence, water-dissolving stone at an almost imperceptible rate, guided by gravity and fracture patterns. Despite its apparent permanence, the Tsingy is still changing. Erosion continues, spikes thin, sections collapse, new fissures open. Over geological time, the entire plateau will eventually be reduced to rubble, its sharp edges worn away. For now, it remains in a dramatic intermediate state, neither smooth nor destroyed, but sharpened. In 1990, Tsingy de Bemaraha was designated a UNESCO World Heritage Site, recognizing both its geological significance and its biological importance. This designation helped protect the area from large-scale exploitation, though challenges remain. Madagascar faces widespread environmental pressure, including deforestation, poverty, and limited infrastructure. Protecting remote areas like Bemaraha requires resources, enforcement, and local cooperation. Tourism has increased, drawn by the Tsingy's surreal appearance. Walkways and bridges allow controlled access, minimizing damage while enabling observation. Even so, the environment is fragile. A single misstep can break vegetation that took decades to establish. The Tsingy does not forgive carelessness. There are no myths of monsters hidden within the stone forest, but local knowledge treats the area with respect. Its difficulty and danger are understood. It is not land to be taken lightly. Standing within the Tsingy de Bemaraha produces a sense of scale that is hard to articulate. The spikes feel close, enclosing, yet the system extends far beyond sight. Every direction leads to more stone, more voids, more vertical complexity. There's no horizon in the usual sense. Vision is blocked by rock walls that rise and fall unpredictably. Orientation depends on sound, light, and careful movement. The sky appears in fragments, narrow slivers between pinnacles. Clouds pass overhead, briefly visible, then gone. Sunlight strikes stone at sharp angles, casting deep shadows that shift slowly through the day. Heat builds quickly. The limestone absorbs and reflects sunlight, raising surface temperatures. Shade exists only in narrow corridors and caves. Moisture is scarce above ground. At night, the Tsingy becomes nearly impenetrable. Darkness fills the gaps. Navigation without artificial light is impossible. The stone forest returns to silence, broken only by insects and distant animal calls. In a world increasingly shaped by human activity, Tsingy de Bemaraha stands as a reminder of what landscapes can become when left to natural processes alone. It's not beautiful in a gentle way. It does not invite comfort. Its power comes from severity and complexity. The Tsingy shows that erosion does not always soften landscapes. Under the right conditions, it sharpens them. Water, given enough time, can turn solid plateaus into knives. Tsingy de Bemaraha is not a place of movement, but of resistance. It resists settlement. It resists agriculture. It resists simplification. Life here survives not by dominating the environment, but by fitting into its cracks. The stone forest of Madagascar is not a ruin of something that once stood tall. It is the exposed skeleton of an ancient surface, carved down until only its hardest lines remain. As long as rain continues to fall and limestone continues to dissolve, the Tsingy will evolve, slowly, relentlessly. And in western Madagascar, beneath the sun and above hidden rivers, the land will remain sharp, fractured, and alive, standing as one of the clearest examples of how time can turn solid ground into something almost unrecognizable, not through violence, but through patience. The mountain that time left behind. At the meeting point of Venezuela, Brazil, and Guyana, a colossal wall of stone rises abruptly from the rainforest. Its sides are sheer, nearly vertical, stretching hundreds of meters straight up into the clouds. The summit is flat, broad, and frequently hidden by mist, as if deliberately concealed from the world below. Water spills endlessly from its edges, falling in thin white ribbons that vanish before reaching the forest floor. This is Mount Roraima, a mountain so ancient, isolated, and self-contained that it feels less like part of Earth's surface and more like a fragment of a different era, left behind while the rest of the planet moved on. The Mount Roraima is one of the most famous tepuis, tabletop mountains found in the Guiana highlands of northern South America. These formations are among the oldest exposed geological structures on Earth. Mount Roraima itself rises to about 2,910 meters above sea level, but its true scale is revealed, not by height alone, but by isolation. Its vertical cliffs separate the summit completely from the surrounding lowlands, creating a natural fortress that has remained largely untouched for millions of years. To understand Mount Roraima, it is necessary to step far back in time, far beyond human history, beyond the age of mammals, and even beyond the age of dinosaurs. The rock that forms Mount Roraima is part of the Roraima Group, a massive sandstone formation laid down nearly 2 billion years ago during the Precambrian era. At that time, Earth's surface was dominated by shallow seas, primitive life, and a vastly different atmosphere. The sediments that would become Roraima were deposited layer by layer, compacted and cemented long before complex life emerged. For hundreds of millions of years, these layers remained buried. Then tectonic forces lifted the Guiana Shield, one of the planet's most stable continental cores. Unlike regions shaped by violent folding or collision, this landmass rose slowly and resisted deformation. Over immense spans of time, erosion stripped away softer surrounding rock, leaving behind isolated remnants of the original plateau. These remnants became the tepuis. Mount Roraima is one of the largest and most dramatic of them. Its cliffs rise between 400 and 1,000 meters almost vertically, making access to the summit extremely difficult. For most of its history, the plateau was completely cut off from the surrounding world, accessible only to wind, rain, and time. That isolation shaped everything that exists on top. The summit of Mount Roraima covers roughly 34 square kilometers, forming a strange, eroded landscape of rock pools, jagged stone, shallow valleys, and scattered vegetation. The ground is uneven, pockmarked with hollows filled by rainwater. Mist drifts constantly across the surface. Temperatures are cool compared to the lowlands, and weather can change within minutes. Rain falls frequently, sometimes daily, but the porous sandstone allows water to drain quickly. Nutrients are scarce. Soil is thin or non-existent. These conditions are hostile to most plant life, and yet life persists. More than a third of the plant species found on Mount Roraima's summit are endemic, meaning they exist nowhere else on Earth. Some evolved from ancestors that once lived across the ancient plateau before erosion isolated the tepuis. Others adapted uniquely to the summit's extreme conditions. Carnivorous plants thrive here, including pitcher plants that trap insects to supplement nutrient-poor soil. Mosses and lichens coat rock surfaces. Small shrubs cling to cracks where organic material accumulates. Everything grows slowly, shaped by scarcity. Animal life is limited, but equally specialized. Small frogs, insects, and invertebrates exist only on the summit or on nearby tepuis. Some species show little resemblance to relatives below, having evolved in isolation for millions of years. In evolutionary terms, Mount Roraima functions like an island in the sky. Water defines the mountain's character. Rain that falls on the summit has nowhere to flow except outward. It spills over the cliffs in countless waterfalls, many of which evaporate before reaching the forest below. This constant runoff contributes to the cloud forests and river systems surrounding the mountain. One of the world's highest waterfalls, Angel Falls, lies not far away, another product of the same geological system. The tepuis act as natural water towers, feeding rivers that shape the region. For the indigenous Pemon people, Mount Roraima holds deep spiritual significance. They regard the tepuis as sacred places, remnants of a mythical tree that once bore all the fruits of the world. According to legend, when this tree was cut down, its trunk fell and became Mount Roraima, while its branches scattered across the land as other tepuis. These stories reflect an intuitive understanding of the mountain's singular nature. Long before geology offered explanations, people recognized that this place was different, older, more powerful, and separate from the land below. European awareness of Mount Roraima came relatively late. In the 19th century, British explorer Sir Everard M. Thurn led one of the first recorded ascents, reaching the summit in 1884. His accounts described a strange, almost alien world: black rocks, shallow pools, and constant mist. These descriptions influenced popular imagination. Arthur Conan Doyle's novel, The Lost World, published in 1912, was inspired in part by Mount Roraima and other tepuis. The idea of an isolated plateau harboring ancient life captured public attention and reinforced the mountain's reputation as a place where time stood still. In reality, Mount Roraima does not preserve dinosaurs or prehistoric monsters, but in a geological and evolutionary sense, it does preserve deep time. The summit ecosystem represents a lineage of life shaped by conditions that no longer exist elsewhere. Climbing Mount Roraima is not a technical ascent in the mountaineering sense, but it is demanding. There's only one practical route to the summit, a natural ramp on the southwestern side. Even this path requires days of trekking through rainforest, rivers, and steep terrain. Weather is a constant challenge. Heavy rain can turn trails into mud. Fog reduces visibility to meters. Winds at the summit can be relentless. There's no shelter beyond what the rock provides. Once on top, movement is slow and careful. The terrain is uneven and disorienting. Landmarks are subtle. GPS and guides are essential. There are no trees tall enough to provide reference points. The landscape feels unfinished, eroded into strange shapes that resemble ruins or abstract sculptures. Scientifically, Mount Roraima is invaluable. It offers insight into early Earth geology, long-term erosion processes, and speciation driven by isolation. Studying the tepuis helps scientists understand how landscapes evolve when tectonic stability allows erosion to dominate over uplift. The mountain also serves as a natural laboratory for climate research. Changes in rainfall patterns, temperature, and cloud cover directly affect the summit ecosystem. Because species here are highly specialized, even small shifts can have significant impacts. Climate change poses a growing threat. Rising temperatures could alter cloud formation, reducing moisture available to summit plants. Changes in precipitation could affect water retention in rock pools. Because these species cannot migrate downward, conditions below are too different, they are particularly vulnerable. Tourism adds another layer of pressure. Increased foot traffic can damage fragile vegetation and thin soils. Waste management is challenging in such a remote environment. Conservation efforts aim to balance access with protection, but enforcement is difficult. Despite these pressures, Mount Roraima remains remarkably intact. Its cliffs still deter most intrusion. Its weather still dictates terms. Its summit still feels separate from the world below. At night, when clouds briefly clear, stars stretch across the sky with extraordinary clarity. The absence of artificial light makes the summit feel truly remote. Sounds are muted. Wind, distant water, the occasional movement of insects. There's no sense of civilization here. Standing on Mount Roraima, it becomes clear that this mountain is not impressive because it is tall, but because it endured. It survived continental drift, climate shifts, and mass extinctions. It watched forests rise and fall below its cliffs while remaining largely unchanged. The tepui is not frozen in time. It is slowly eroding, grain by grain, But erosion here works on timescales so vast that change feels invisible. Every year, the mountain loses a fraction of itself, carried away by water and wind. Over millions of years, even Mount Roraima will disappear. That inevitability does not diminish its significance. It enhances it. Mount Roraima is a reminder that Earth's surface is not uniformly young or dynamic. Some places are survivors, remnants of ancient worlds that persist not because they resist change, but because they change slowly enough to remember. In the clouds above the Amazon, at the edge of 3 nations, Mount Roraima stands as one of the clearest expressions of deep time visible to the human eye. A mountain that did not grow upward, but remained while everything around it fell away. A place where isolation became preservation. A fragment of Earth's distant past, still standing, quietly, patiently, above the forest below. The caves that exist only for a season. In southeastern Iceland, where glaciers descend from a vast ice cap and grind slowly toward the sea, there are caves that form, glow, and disappear without leaving a trace. Their walls are blue, sometimes pale and glass-like, sometimes deep and saturated, as if light itself has frozen into solid form. The ceilings arch overhead in smooth curves, etched with lines that resemble flowing water suspended mid-motion. For a brief window each year, these caves exist. Then they collapse, melt, or vanish entirely. This is the world of the Skaftafell ice caves, among the most temporary and visually striking natural formations on Earth. The Skaftafell ice caves are found within Vatnajökull National Park, beneath the tongues of glaciers flowing from Vatnajökull, the largest ice cap in Europe by volume. Skaftafell itself was once a separate national park before being incorporated into the larger protected area. The region sits at the intersection of fire and ice, volcanoes beneath glaciers, meltwater carving paths through frozen mass, and climate forces shaping everything continuously. Unlike rock caves, which can persist for millions of years, ice caves are ephemeral. They are not carved once and preserved. They are rebuilt every winter and destroyed every summer. Each season produces a new system of tunnels, chambers, and arches, shaped by meltwater, pressure, and temperature. No 2 winters create the same caves. The formation of the Skaftafell ice caves begins deep within the glacier. During warmer months, meltwater forms on the surface of the ice cap. This water flows downward through cracks and vertical shafts called moulins, carrying heat with it. As it descends, it carves channels through the ice, exploiting weaknesses and fractures. In summer, this flowing water is destructive. It widens channels and hollows, but also destabilizes the ice. Caves formed during this time are unsafe and short-lived. It is only when winter arrives, when temperatures drop consistently below freezing, that these channels stabilize. As water flow slows or stops, and the ice refreezes, the tunnels harden, walls thicken, ceilings solidify, the cave becomes temporarily stable. This is when the ice caves reveal themselves. The defining feature of the Skaftafell ice caves is color. The ice appears blue not because it's colored, but because of its density. Over time, snow compresses into ice, forcing out air bubbles. This dense ice absorbs longer wavelengths of light, reds and yellows, and scatters shorter blue wavelengths back to the eye. The thicker and purer the ice, the deeper the blue. Inside the caves, light enters through thin sections of ice or small openings. It refracts and diffuses, filling the interior with an otherworldly glow. The effect shifts constantly as clouds move, snow falls, or the sun's angle changes. At times, the cave appears softly illuminated. At others, the blue deepens into near darkness. Textures within the caves reveal the glacier's movement. Lines and bands run along the walls, marking layers of snowfall compacted over years or even centuries. These lines bend and stretch, showing how the ice has flowed downhill under its own weight. In some places, the ice is perfectly smooth. In others, it is ridged or scalloped, shaped by turbulent water flow. Small stones embedded in the ice tell of debris carried by the glacier from mountains far above. The sound inside an ice cave is subtle and unsettling. Water drips steadily. Ice cracks softly as it shifts. Occasionally, deeper groans echo through the structure, reminders that the glacier is moving, even when it appears still. Skaftafell's glaciers are outlet glaciers, tongues of ice flowing outward from the Vatnajökull ice cap. They move slowly but relentlessly, advancing and retreating depending on climate conditions. As they move, they grind rock beneath them, carving valleys and transporting sediment. The ice, caves form at the glacier's margins, where meltwater exits the ice. These exit points shift from year to year, meaning caves rarely form in the exact same location twice. This unpredictability is part of what makes the Skaftafell ice caves dangerous. Ice caves are inherently unstable. Even in winter, collapse is possible. Temperature changes, increased meltwater flow, or internal stress can cause ceilings to fail without warning. Entire caves can disappear in hours. For this reason, access is strictly seasonal, and typically limited to guided tours led by trained glacier experts. Routes are assessed constantly. Caves deemed unsafe are abandoned, even if they are visually spectacular. The danger is real and non-negotiable. Despite these risks, people are drawn to the caves in increasing numbers. Photographs of glowing blue tunnels circulate widely, often without context. What appears serene and static is, in reality, temporary and fragile. The caves are not meant to be permanent. From a scientific perspective, the Skaftafell ice caves offer rare access to the interior of a glacier. They allow researchers to observe ice structure, meltwater pathways, and sediment transport directly. These observations help refine models of glacier behavior and melt dynamics. They also provide insight into climate change. Vatnajökull is shrinking. Rising temperatures have increased melt rates, altering the balance between accumulation and loss. Glaciers retreat further each year. As this happens, the conditions that form ice caves change. Some winters produce exceptional caves, larger, clearer, more accessible. Other winters produce none at all. Long-term warming threatens to shorten the season during which caves can exist safely. Eventually, some glaciers may become too thin or unstable to form caves at all. This impermanence gives the Skaftafell ice caves a unique significance. They are not just geological features, they are indicators. Their presence, size, and stability reflect broader environmental conditions. Human history in the Skaftafell region is shaped by adaptation to ice and fire. For centuries, Icelanders lived with glaciers advancing into farmland, rivers changing course, and volcanic eruptions reshaping the land. Glaciers were not distant phenomena. They were immediate forces affecting survival. In Icelandic folklore, glaciers were often associated with spirits or hidden beings. Their unpredictable behavior inspired caution and respect. Entering a glacier was not taken lightly. Modern equipment and knowledge have made access possible, but not safe in an absolute sense. The glacier still dictates terms. Inside a Skaftafell ice cave, the sense of time becomes distorted. The ice beneath your feet may be hundreds or thousands of years old. The cave around you may be days or weeks old. The entire structure may cease to exist before the season ends. Every visit is temporary. Every photograph captures something that will not be seen again. At the same time, the glacier itself has endured for millennia. While individual caves vanish, the system that creates them persists, at least for now. This contrast between longevity and fragility defines the experience. Light, ice, water, and gravity interact in precise ways to produce beauty that cannot be preserved. There's no way to freeze an ice cave in time. Any attempt to do so would destroy it. When spring arrives, temperatures rise. Meltwater returns in force, channels widen, ceilings thin. Eventually, the cave collapses or floods, erasing its interior completely. By summer, there may be no sign that the cave ever existed. The glacier absorbs the evidence. The cycle begins again. Skaftafell's ice caves remind us that some of the most extraordinary natural formations are not meant to last. They exist briefly, shaped by exact conditions that align for a moment and then dissolve. In a world where permanence is often valued, these caves offer a different lesson. Beauty does not require endurance, meaning does not require preservation. The caves are powerful precisely because they are temporary. They show us ice not as static mass, but as moving, breathing material, responding constantly to heat, pressure, and gravity. They reveal the interior of glaciers that are otherwise inaccessible. They also confront us with change. As glaciers retreat, the caves change with them. What we see now may not be possible to see in the future. Standing inside a Skaftafell ice cave, surrounded by blue light and silent walls, it becomes clear that this is not a monument, but a moment carved by meltwater, a moment held by cold, a moment already passing. The cave does not belong to the visitor. It belongs to the glacier, And the glacier belongs to time. In southeastern Iceland, beneath the immense weight of Vatnajökull, the ice caves appear briefly each winter, shimmering, unstable, unforgettable, before vanishing back into the frozen mass that created them. They do not wait to be remembered. They exist, and then they are gone. The stone that flows without moving. In the remote borderlands of northern Arizona, where the desert stretches quietly between states and roads, thin into dust, there's a formation that looks like motion captured in rock. Bands of red, orange, cream, and pale pink curve across the ground in smooth, continuous lines. The stone folds, dips, and rises as if frozen mid-movement, resembling waves rolling across a solid sea. There's no water here, no sound of erosion in action, and yet everything about the landscape suggests flow. This is the wave, one of the most visually precise and geologically revealing sandstone formations on Earth. The wave is located within the Coyote Butte's north area of the Parai Canyon Vermilion Cliffs Wilderness, straddling the Arizona-Utah border. It lies far from highways, visitor centers, or permanent facilities. Reaching it requires navigation across open desert, guided only by terrain and landmarks. This isolation is intentional. Access to the wave is strictly limited, not because it is fragile in the immediate sense, but because its survival depends on restraint. The wave exists because of conditions that no longer exist. To understand it, one must go back nearly 190 million years, to the early Jurassic period. At that time, this region was not desert, but a vast sand sea, an enormous erosion comparable in scale to the modern Sahara. Wind dominated the landscape, pushing dunes hundreds of meters high across an open basin. These dunes were not static. They migrated constantly, their shapes shifting with the changes in wind direction, speed, and sand supply. As dunes moved, layers of sand piled up at angles, forming cross-bedding, slanted layers within the dune structure that recorded the direction of ancient winds. Over time, these dunes were buried beneath additional sediment. Pressure compacted the sand. Minerals dissolved in groundwater cemented grains together. The dunes hardened into sandstone, preserving their internal structure in remarkable detail. This sandstone is known as Navajo sandstone, one of the most widespread and recognizable formations in the American Southwest. It forms the backbone of many iconic landscapes, including Zion National Park, Canyonlands, and parts of the Grand Canyon. For millions of years, the Navajo sandstone lay buried. Then, tectonic uplift raised the Colorado Plateau, exposing these ancient layers to erosion. Wind, rain, temperature changes, and gravity began stripping away softer material, slowly revealing what had once been buried. The wave formed where conditions aligned precisely. The sandstone here is exceptionally fine-grained and uniformly cemented, allowing it to erode smoothly rather than breaking apart. At the same time, the region experienced enough erosion to remove overlying layers, but not so much as to destroy the underlying structure. Water played a critical role, not as a river or flood, but as intermittent rain. When rain falls on exposed sandstone, it seeps into tiny pores and fractures. As water evaporates, it leaves behind minerals that can both strengthen and weaken rock, depending on concentration. Repeated cycles of wetting and drying slowly loosen grains at the surface. Wind then removes those loosened grains, sculpting the rock millimeter by millimeter. Over immense spans of time, this process accentuated the natural curves of the cross-bedded layers, carving the flowing shapes seen today. The color bands of the wave are not painted by light alone. They are embedded in the rock. Variations in mineral content, especially iron oxides, create subtle differences in hue. Red layers indicate higher oxidation. Lighter bands reflect lower concentrations or different cement chemistry. What makes the wave visually unique is the continuity of these bands. Lines curve without interruption, wrapping around rises and dipping into troughs with mathematical smoothness. There are no abrupt breaks. The rock appears intentional, almost designed. But nothing here was designed. The wave is a coincidence of preservation. Countless dunes once existed like this. Most were destroyed, distorted, or buried beyond recognition. The wave survived because erosion removed everything else around it at just the right pace. From above, the formation resembles a sheet of striped fabric draped across the land. From ground level, the effect is immersive. The lines guide the eye, pulling attention forward and downward. There are few sharp edges. Everything curves. Walking across the wave requires care. The sandstone surface is smooth but fragile. A single footprint can leave a visible mark. Oils from skin can alter surface chemistry. Rain can darken the stone temporarily, enhancing contrast but also increasing vulnerability. Because of this fragility, land managers restrict access to just 64 people per day, selected through a lottery system. There are no guardrails or signs at the site itself. Protection relies on education and respect, rather than enforcement. The wave's remoteness contributes to its mystique. There's no trail leading directly to it. Visitors must navigate several kilometers of open desert, crossing slick rock, sandy washes, and low ridges. GPS devices help, but the landscape can be disorienting. This difficulty is deliberate. It ensures that only those prepared and aware of the risks reach the formation. The desert here is unforgiving. Summer temperatures regularly exceed 40 degrees Celsius. There's little shade, water sources are non-existent, weather can change rapidly, with thunderstorms producing flash floods in nearby washes. Despite these hazards, people are drawn to the wave in increasing numbers. Images circulate widely, often detached from context. The formation appears small in photographs, but in reality, it occupies a broad area, rising and falling over dozens of meters. There is no single viewpoint that captures it fully. Understanding the wave requires movement, walking its contours, seeing how lines align from different angles. The experience is physical as much as visual. Scientifically, the wave is valuable because it exposes dune crossbedding with unusual clarity. Geologists study it to understand wind patterns in ancient deserts, sediment transport, and erosion mechanics. Each curve records a former dune face, frozen in stone. The formation also challenges assumptions about erosion. Rather than producing jagged cliffs or chaotic shapes, erosion here refined structure. It did not destroy order, it revealed it. Human history in this region extends back thousands of years. Indigenous peoples, including ancestral Puebloan and Southern Paiute groups, traveled through the area, using seasonal routes and water sources. The wave itself was not a focal point, but part of a broader landscape understood through experience, rather than spectacle. Modern recognition came late. The wave was known to locals and geologists, but it gained international fame only in the late 20th century as photography and travel media spread its image. Increased attention brought pressure, prompting strict management. Unlike national parks with infrastructure and staff, this wilderness relies on minimal intervention. There are no restrooms, no trash bins, no fences. Visitors must carry everything in and out. Any damage remains visible for decades. The wave is not static. Erosion continues. Rain smooths edges. Wind removes grains. Freeze-thaw cycles expand microfractures. Over geological time, the formation will change and eventually disappear. Its current form is temporary. That impermanence is part of its significance. The wave exists at a precise moment in Earth's long timeline, exposed, intact, and recognizable. Past and future versions differ. Light transforms the formation throughout the day. Morning light softens contrast, emphasizing pale creams and subtle pinks. Midday light intensifies reds and sharpens shadows. Evening light warms the stone, deepening color and flattening relief. After rain, the rock darkens dramatically, revealing details otherwise invisible. Bands appear richer, surfaces look polished, but moisture also increases fragility, making careful movement essential. At night, the area becomes silent. With no artificial light nearby, stars fill the sky. The Milky Way arches overhead. The rock fades into darkness, its curves invisible without light to reveal them. In these moments, the wave becomes abstract, present but unseen, defined by memory rather than form. What makes the wave compelling is not scale or danger, but precision. It is a landscape that appears to have intention without intent. Every line aligns. Every curve feels purposeful. Yet the processes behind it are blind. Wind does not aim. Water does not plan. Stone does not remember. And yet, together, they produce something that feels almost deliberate. The wave is not unique because it is rare in theory, but because it is rare in practice. Conditions like those that formed it existed widely in the past. Preservation like this did not. Most ancient dunes were erased. This one remained. Standing on the wave, it becomes clear that landscapes are not defined only by what is added, mountains built, lava piled, but by what is removed. The wave is subtraction made visible. Layer by layer, erosion stripped away everything except the pattern. In the deserts of Arizona, where emptiness often dominates, the wave reveals hidden order beneath apparent simplicity. It shows how time, when allowed to work uninterrupted, can produce precision without intention. The stone does not move, the wave does not break, and yet motion is everywhere, captured, preserved, and waiting to be seen. As this journey ends, these places remain, quiet records of forces far older than us. Thank you for watching Unearthed Secrets. Until next time, keep looking closer beneath the surface of our world.